Do you love programming and want to turn your talent into a career? How about becoming an application developer in the field of industrial automation? The market for industrial and process automation is huge, and it's only going to grow in the coming years. Maybe you're not familiar with the traditional PLC technology and don't want to learn outdated PLC languages. Well, I've got something perfect for you. UniversalAutomation.org has introduced a new way of programming using the standard IEC 61499. Unlike the old PLC standard 61131, which still runs cyclically, where variables are scattered in different sections and one programmer can barely understand another one's code, IEC 61499 uses an event-driven approach combined with object-oriented programming. If you like programming languages like C++, C#, Java, JavaScript, or Python, you will feel right at home. The platform I'll use today is EcoStruxure Automation Expert, Schneider Electric's software-defined automation platform. I'll show you how quickly you can create and test an automation application using EcoStruxure Automation Expert. To make this video enjoyable, you should be familiar with the basics of EAC 61499 and EcoStruxure Automation Expert. But don't worry, I'll guide you through everything step by step. In this video, we'll program a booster pump system following the ISA 88 standard. ISA 88 is an international standard for modeling and controlling batch processes. If you're not familiar with ISA 88, that's okay. You'll still be able to follow along. Our system is simple. A water tank that can be filled externally. 2 pumps for pressure control, a pressure sensor, a level sensor in the tank. The entire system is considered a unit which consists of multiple equipments such as the tank, pumps, and sensors. Here's the basic logic. If the pressure drops, pump 1 starts. If the pressure continues to fall below a certain threshold, pump 2 kicks in to help maintain pressure. Here's how we'll proceed. I'll program small parts and test them immediately. For testing, we need a simulation environment which I'll create using symbolic links. Enough talking, let's start coding. I've created a new full solution project called Tank Unit and imported a template cat called generic OOP. If you don't have this template, you can easily create it yourself. It consists only of frames. Left, logical inputs, right, logical outputs. Middle, code for functional behavior, operation management, and interlocks and permissions. A unit consists of 1 or more equipments, and each equipment is a child of the unit. You'll find the children of a cat on the right side, and at the bottom you'll see the electrical inputs and outputs. I'll create a new cat called tank and remove the automatically generated events and variables. The tank is simple. It only has one analog input called level, which I'll place under the field interface frame. Next, I'll create a visualization, a rounded rectangle for the tank, a vertical slider for the analog input inside the rectangle. I configure the analog input Measurement range up to 6 meters, low signal at 0.9 meter. To keep things organized, I'll create two folders. Equipment In the unit folder, I create a new cat called tank unit, remove the auto-generated IOs and events, and copy the frame structure from generic OOP. The tank unit consists of two pumps and one tank. The pumps come from the library and the tank is the one we just created. Now I'll build visualization for the tank unit based on the BIND diagram. I'll add the pressure sensor as an analog input under field interfaces and include it in the tank unit visualization. Then I'll create a new HMI with a resolution of 2080 by 800. The first page will be called tank unit. Next, I'll insert the tank unit cat into the system application and map it to the resource. Now the tank unit appears as an instance under Kent instances, and I can add it to the HMI. Under deployment, I'll switch to local test since we're not using real hardware and then start this runtime simulation. Under System Devices, I'll add DPAC full init to initialize the resource. I load the project to check for errors and then adjust the parameters for the pressure sensor. To test the code, I'll create a new CAD called Simulation. This CAD is not part of the tank unit and isn't directly connected, so I can easily remove it later by deleting the resource mapping. Communication between the two will be done using symbolic links. I want to read the analog set point speed of the pump. First, I need to find the signal. But I realize I used the wrong motor CAD without analog speed control. No problem, I'll change the type. Then I'll re-add the pumps to the tank unit visualization and draw a thick pipe to represent the supply network. The signal name is pump1.cmdspeed.aout. The symbolic link string starts with res0 followed by tank unit pump1 cmd speed aout. Make sure to respect case sensitivity. The type is real. I'll write this value back to the pump's analog feedback signal. Res0, tank unit, pump1, FB speed, A in. I'll also create an alarm page to acknowledge pump alarms. The page will include an alarm banner and I'll adjust the column width. I load the project into the runtime and see an alarm on the pump. I'll acknowledge the alarm and set the pump to operation mode so I can manually set the speed. The pump starts briefly and then trips because digital feedback signal is missing. I'll add that now. Both symbolic links are of type bool. The test looks good. The pump reaches the set point immediately. To make the simulation more realistic, I'll add a delay for the digital feedback signal and a basic block for the actual pump speed. Unfortunately, there's no PT1 block available, so I'll quickly build one using AI. I'll test the block. The actual value changes too fast, so I'll slow it down. Now it looks better. I'll integrate the PT1 block into the simulation and call it cyclically using the eCyclic block. I'm testing the first pump now, and the actual speed behaves more realistically. I need to do the same for the second pump, but with copy-paste, that's quick. I test the second pump, and it looks good. However, something bothers me. When the set point is 0, the pump should stop immediately. I'll adjust that now. The test looks better now. Next, I need a tank level simulation. For this, I'll create an IDIS object with a variable called level simulation. I also need a symlink source block to write to the analog input for the tank level. This string will be res0 tank unit level raw PV A in. I'll simulate filling the tank using a slider in the HMI. For the level calculation, I'll create a basic block called tank level sim BAB. The tank level will change based on two variables, tank filling and tank release. I'll rename the instances to more meaningful names. Testing now, the level changes too quickly. I'll divide by 1000 to slow it down. Testing again. When I increase the slider, the level rises. Perfect. However, the tank should start at 50% full when the program runs. Now the initial level is 3 meters at startup. I start the pump and the level should drop, and it does. With the second pump, the level drops even faster. Great! Now I need to simulate pressure. I'll add a new variable called pressure simulation and use a slider for this as well. Next, I'll set up interlock conditions for the pumps. I'll create a new CAD called tank unit lock. Both pumps will share the same interlock variable. Each pump needs an iLock cont item. I'll add the new cat to the tank unit and link it to the pumps. The interlock condition is the low signal from the tank. The pumps should only run when the tank is almost empty. I'll expose the low signal from the tank object as an input for the interlock variable. Testing now, I set the low level to 2.9 meter and start the pumps. The interlock activates, but I made a mistake. It blocks the pump from turning off, not on. I'll fix that quickly. Now the pumps are correctly interlocked. But there's another issue. As soon as the level rises slightly, the pumps turn on and then off repeatedly. That causes constant switching. I'll fix that next. And here is the interlock message. To prevent pumps from restarting immediately, I need a permission condition. I'll create a new object called tankUnitPermission using tankUnitLock as a template. I'll adjust the text for the permission message. The permission condition will be calculated in this object using two variables, permission level and tank level. I'll expose tank level from the tank object. Permission level should be configurable, so I'll use the ID subject from the tank unit. I create a parameter button that opens a faceplate called FP parameter. The permission level variable will be persistent. If tank level is greater than permission level, the pump is allowed to start. Testing now, I set permission level to 2.9 meter. Even though the pump lowered the level below 2.9 meter, it keeps running. However, it can't restart until the level rises above 2.9 meter again. Perfect. Now we need the logic for normal operation, the pressure control. I'll create a new object called tank unit FB and copy the frame from the generic OOP template. Inside this object, I'll add a PID controller called PID pump 1. The controller needs a set point and a process value, which I'll expose as inputs. I'll place this object inside tank unit under functional behaviors. The instance name will be functional behavior. The set point will come from the parameter faceplate, so I'll use an encode analog block. The pump also needs an automatic mode enable signal. I'll generate this signal automatically when the PID output is above 5%. I'll add the PID parameter and the set point to the faceplate. The actual pressure slider should go up to 8 bar, so I'll set the max value to 8 and the engineering value to 100. The set point should also be persistent. I reload the project and clear all persistent data. Testing now. Set point equals 3 bar, actual pressure equals 2 bar, pump 1 ramps up, pump 2 has no logic yet, so it stays off. I'll increase the pressure slightly above the set point, the pump slows down, increase more, the pump stops. Lower the pressure, the pump starts again. Perfect. Now I'll integrate pump 2. Since I have extra adapters, I need to split the input signal using a split analog block. Pump 2 should only start if the pressure drops significantly. I'll use a hysteresis block for this with two new variables, start pump 2 and stop pump 2. The logic is simple. If the interlock output is active, reset it when the actual pressure falls below start pump 2. If the actual pressure rises above stop pump 2, the pump is no longer needed and is locked. To get the actual pressure, I use a decode analog block and another split analog block. I'll set start pump 2 and stop pump 2 in the parameter faceplate. I'll add the second PID controller and the start-stop values for the pump 2 to the faceplate. Testing now. Pump 2 should start when the actual pressure drops below 2.4 bar. I slowly increase the pressure. Pump 2 locks when the pressure rises above 2.8 bar. I can also see the interlock reason from the second PID controller. Testing again. It works perfectly. That's enough for today. There are many more exciting topics to dive into, such as IIoT integration, high availability architectures, cybersecurity concept, advanced visualization techniques, cross-platform communication, creating hardware-tailored CADs, and much more. EcoStruxure Automation Expert is a complete and independent ecosystem within the world of industrial automation. If you like to learn more about these topics, make sure to click subscribe. And if you enjoyed this video, I would really appreciate a thumbs up. Thanks for watching and see you in the next one.